In section 1.5, we talk about the idea of a basis and dimension in Rn, and we're going to talk about some other concepts like linear independence. But the question that we want to start with is, can any vector in R2 be made with a linear combination of these two vectors, 1, 0, and 0, 1? And along with that question, we're also going to ask at the same time, can any vector in R2 be made with a linear combination of the vectors 1, 0, and 2, 0? Okay, so let's see what we're even talking about when we say this. So for example, let's think about the vector 13, 4. It could be sitting maybe like right up here somewhere. And so there's that vector. And we think, can it be made with a combination of these two? And yeah, it's not too hard to see how that would be made. You could take this as 13 times 1, 0 plus 4 times 0, 1. So 13, 4 can be made with a linear combination of those two. Similarly, we can ask over here, could 13, 4 be made with a linear combination of 1, 0 and 2, 0? So let's get a picture of, so 13, 4, and maybe about right here. And as we try to think of a way to build that vector just from these two, it isn't immediately obvious, and it's not obvious because it's not possible. So it starts out okay. You could say, okay, 13 times 1, the vector 1, 0. But what could we multiply by the vector 2, 0 to get that x2 element, the 4? And you just never will. It won't work out. So this isn't going to work. So the answer to this question up here is definitely yes. You can build the vector 13, 4. In fact, you could build any vector in R2 just from 1, 0 and 0, 1. But over here, it wasn't possible. There was too many missing pieces, and so these were two vectors that you couldn't build it. These were two vectors that you could construct really any vector in R2 from. And so we've seen this word before, but we say that 1, 0 and 0, 1 span R2. And we say that 1, 0, 2, 0 don't span R2. It wasn't enough. They couldn't build certain vectors. We also are going to say that 1, 0 and 0, 1 are linearly independent. And this is the first time that we've talked about this phrase. What it means is that, well, I'll give you the mathematical definition of linear independence first. And it is that P times 1, 0 plus Q times 0, 1. If this equals 0, 0, so these were our two vectors that we're talking about being linearly independent. If this equals 0, 0, this only happens, or it only has P equals 0 and Q equals 0 as a solution. let me show you an example of, so I'm telling you those two vectors are linearly independent. Let me show you an example of two vectors that aren't linearly independent and how they fail this test. So this is an example of being not linearly independent over here. And these are fairly obvious ones why they're not linearly independent. 2, 4, and 1, 2 are not linearly independent. And if we tried to have p times that first vector plus q times this second vector equaling 0, 0, it's definitely true that 0 times 2, 4 plus 0 times 1, 2 works. But there's another way to make that work. You could also say 1 times 2, 4 plus negative 2 times 2, 4 equals 0, 0. And the fact that this bottom one is also a solution where you have a p equals 1 and a q equals negative 2, this makes it so that these two fail to be linearly independent. You can see we haven't really, I mean, we're just introducing this idea, but being linearly independent, you can see that really 2, 4 is just a scalar multiple of this guy. They're definitely dependent on each other. They're very related linearly. And here is the formal definition of linear independence. You have a set of n vectors, and they are linearly independent if c1 v1 plus c2 v2 plus cn vn equals the 0 vector. That is only true if all of your constants are 0. And we'll also give the formal definition of a span. You have a set of vectors v1 through vn, and we say that they span a space if every vector in that space can be expressed as a linear combination of those vectors. And those two terms are going to lead to a third term. So any set which spans a set and is linearly independent is called a basis for a space. And a basis is basically like the most efficient framework of a vector space. So this is the picture from page 1 of a framework of a building. And think of a basis as a framework for a vector space. You're going to be able to create any other vector from your basis, and there's nothing extra. So for example, 1, 0, 0, 1 is a basis for R2. And graphically, we can see that as we think about, the vector 1, 0 is about right there, and the vector 0, 1 is sitting right here. And any other vector in R2, we can build from that. Similarly, R3 has a basis, and the basis for R3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. I should say a basis for R3. We're going to see that vector spaces have more than one basis. So there's the first vector in our basis. Here's a second vector. And then here's that third vector. And any other vector in R3 can be built from those three. Okay, so these two examples, these are the standard bases for R2 and R3. So that you can see them visually. And it's similar for Rn. We can't geometrically visualize R4, R5, but algebraically they're standard bases are the same. Similarly for Rn. And then we need to make the point, but they aren't the only bases for those vector spaces. They aren't the only bases, but they're definitely important ones, and we call them the standard basis, or for each vector space are the standard bases. Okay, when I say that they're not the only ones, for example, I'm going to tell you that the vector set 157, 203, 110 is also a basis for R3. Is also a basis for R3. And remember, what are the two qualifications to be a basis? You have to span the set and you have to be linearly independent. For example, and so this is just a reminder that there are many bases of R3. We want to remember that. Okay, let's dive into this example though. I'm telling you that it's a basis, and so let's see if we can show that it's linearly independent. So in this example, we want to show that this set of these three vectors that I just told you were a basis for R3, that this set is linearly independent. And we have to think, how would we show that? The test for linear independence has to do with a bunch of constants, you know, a constant multiplied by this, plus a constant multiplied by this, plus a constant multiplied by this. If that equals the 0, 0, 0 vector, then the only possibility is that those constants were all 0. How do we go about proving that? Well, let's write down what I just said and take a look at where we can go from there. So here's the equation that we're interested in, and it's not immediately obvious to me why it would have to be that P, Q, and R are 0. Hopefully they are, because that's the only way to show linear independence. But this is where we start, and what I'm going to do is just try to solve this equation, or we're going to work the constants through the vectors and see if any ideas pop out. So let's see, if I am going to multiply each of those vectors by the constants and add them together, I'll get P plus 2Q plus R is my first element once everything gets added together. And my second element would be 5P plus 0Q plus 1R. And my third element will be 7P plus 3Q plus 0R. So all I was doing was I was multiplying each of these constants through the vector and then adding them together all in one step there. Okay, and that has to equal 0, 0, 0. Well, I've got three variables, and it looks like just setting these two vectors equal to each other, I've got three equations. P plus 2Q plus R equals 0. Then 5P plus R has to equal 0. This is because corresponding parts of equal vectors have to be equal. And 7P plus 3Q equals 0. I have a system of equations here. I'm going to put it in a matrix and solve that matrix and see what comes out. So this first equation in a matrix looks like this. The second equation is going to be put in as that, and this equation is going to be put in as that. And I'm going to take this matrix and do row echelon form. And once I do row echelon form, this is harking back to the first two sections of our class. All of these here, these first three columns tell me that things worked out great, and I'm going to get one solution. And the solution I'm getting is it's not C1. How about P is equal Okay, this first line tells us P equals 0. Then we know that Q equals 0. And reading this third line, R equals 0. And we have one solution. There's not multiple solutions here. It's just that one solution. And so the test for linear independence has been met, because that was the only solution to our system of equations. So this test for linear, not linearly, how about just linear independence is met. Let's just review really quickly the logic of this example. We're asked to show this set of this basis, or this set of vectors, is linearly independent. And so far the only thing we really know about linear independence is that if you take a linear combination of those vectors and it equals 0, 0, 0, the only way for that to happen is for these constants to equal 0. That's what it means to be linearly independent. And so we had set up this equation, and once that was there, it wasn't obvious that that had to be true, but we knew that we could combine this left side into one vector just by multiplying things through and adding things together. And so we got this one vector equals this one vector. At that point, we know that each part has to be equal. And then that put us into a system of equations. Once we're in a system of equations, this is just like, old school. We know how to do this. We put this into a matrix. We go through reduced or row echelon form. And in this case, we came out with one solution. This first part of the matrix, being an identity matrix, will tell us that the system only has one solution, and this is your solution. So it was only possible that P, Q, and R were going to equal 0. There was no other way to make this true. That's the test for linear independence, and it was met. The next thing I'm going to ask is, and we're going to give some vector, be written as a linear combination of the above three vectors, these. So part A, we were looking at linear independence, and this part B is kind of giving us a taste of the span of these three vectors. It's not a proof that they span R3, but it's going to be kind of just a taste that probably any vector in R3 can be constructed from these three vectors. And I'm just going to pick some weird vector, let's say 17, 2, -5. Could this vector be a linear combination, be constructed from these three? We want to be able to see the feasibility that it's a basis, that it spans the whole set of R3. So we're going to see if a linear combination of our three vectors that we've been looking at can become this vector. And we're going to do the same. We're going to do a similar thing as to what we did up here. We're going to combine this into one vector. We'll come up with a system of three equations in three variables and see if we can solve it for these constants. If we can find constants that make this work, then these three vectors can form a linear combination of this one. Okay, so I've done a few steps in one here. I multiplied those constants through. I combined those three vectors into one vector, and all the while it needs to equal this vector. So this first element needs to equal 17, this element needs to equal 2, and this last element would have to equal -5, which sets us up in this system of equations. We'll do like we have before and put it in a matrix and try to solve this system and see if we really are able to come up with the C1, C2, C3 that will make this work. When I put that system of equations into a matrix and I did reduced row echelon form, I'll show you what I got. So for my first row, I got 1, 0, 0, -55 over 26. For my second row, I got 0, 1, 0, 85 over 26. And for my third row, I got 0, 0, 1, 327 over 26. So totally ugly numbers, but this system was solved, and it was solved where there was a unique solution, and this was our unique solution. Those were the C1, C2, C3s that made it work. And so we find that it was possible to write 17, 2, negative 5 as a linear combination of the three vectors. So it's not pretty, but it's possible. And so this this little exercise is part B. We haven't proven it, but any vector in R3 can be made from the three vectors. They do span R3. This is just a taste of it. It's not a proof at all. It's just one example of a taste of the span. Okay, let's just talk one more time about the logic of what was going on here. Whereas part A, we were talking about linear independence, this question has more to do with the span of those three vectors. How far can they reach? Can they really construct any other vector in R3? And we started by saying, okay, hopefully a linear combination of those three vectors can create this vector. And then it was somewhat similar to part A. We were just going to have to solve this system of equations. We did that, and it was possible. We found three constants that we could multiply by this set and add them together and get this vector. So we didn't prove that those three vectors span R3, but this is a hint that they do, that we really could put any vector in R3 in this position and construct them. So what we were exploring in the last example, in the last couple of pages, was this is a basis for R3. It's the standard basis, and it's easy to see how other vectors are constructed from it. But importantly, this is also a basis for R3. It's no coincidence that this has three elements and this has three elements, and they're both bases of R3. And now we're going to introduce a new term that we'll use. So this fact, the term comes from the fact that the number of vectors in a basis is the dimension of a vector space. So this term dimension is equal to the number of vectors in a vector space's basis. And the dimension of Rn is n. So dimension of R2 is 2, the dimension of R5 is 5. If we were talking about a basis for R5, we would know it would have 5 elements in it, whatever basis it was. You can never get a basis of R5 that has 6 elements or 4 elements in it. In our last example for this section, we're going to find a basis for the subspace of solutions to a homogeneous system of equations. And this has so many things that we've learned in it. It's a great problem. So first of all, think of all the things that we've learned that this one example is incorporating. We learned last time in section 1.4 that solutions to a homogeneous system of equations will form a subspace. That's a big deal. And any space, any subspace, which is itself is a vector space, will have a basis. And so this is the first time, though, that we're being asked to find the basis. And we're going to talk about how to do that. So here it is. This is our homogeneous system of equations. It looks like we are sitting inside the vector space R4. So the solutions to the system will be a subspace within R4. And I know you could solve this system on your own if you had to, but I'm going to give you the solution to this system, and from that solution we're going to construct a basis. So here is the solution set to this homogeneous system of equations, and looking at this solution set, we have two parameters, r and s, and what if we pulled out each parameter? So let's see, we would have from if we pulled out an r from each one, the first term has 2r in it, the second term has 0r, the third term has 1r, and the fourth term has 0 r's. At the same time, we'll pull out an s from each term, and the first term has a -1, the second term has a -3s, the third term has no s's in it, and the fourth term has 1 s in it. So hopefully it makes sense how we went from here to here. We're just rewriting the solution as a linear combination of this vector and this vector. We've pulled out the parameters, and that's the key to noticing that this whole set can actually just be constructed from this vector and this vector. So those two vectors are our basis for this solution set, because anything in here can be constructed as a linear combination of 2, 0, 1, 0 and negative 1, negative 3, 0, 1. So our basis for that whole set is this set. This is the framework for the solution set. With these two vectors, I can construct any solution to that homogeneous system. And so we can also say that this subspace has dimension. Let's see, dimension is the number of vectors in a basis, and so this subspace has dimension too. It's a subspace sitting inside of R4, but the subspace itself only has dimension 2 because its basis only has 2 elements in it. So maybe one way to visualize this is we have the set R4. It's a very large set of all the vectors of 4 real elements. And sitting inside of R4 is our smaller sort of subspace of all the solutions to this system of equations. So this is our subspace, and so these are solutions to the above equations, and really this whole subspace can be built by just 2 vectors. This is the framework. I don't know exactly what they look like because these 2 vectors are in R4, but those 2 vectors can build the whole space just through linear combinations. And so this whole subspace can be built by linear combinations of these 2 vectors. Okay, this was a good example. Let's think through it again. The subspace of solutions to a homogeneous system of equations, all of that we learned back in 1.4. And the only new thing is we're trying to find a basis for that subspace. We're actually given the solution, and the sort of clever thing to do was just rewrite that solution as a linear combination of this vector and this vector. And these 2 vectors can construct anything in this set. So we knew that that was a basis for it and that it had dimension 2. So we'll end by reflecting on what new things we've talked about today. We talked about linear independence, and there's a test for linear independence of vectors that we went through. The basis is like the framework of a vector space, and it has to span the space. It also has to be linearly independent, so it's like the most efficient framework of a vector space, and however many elements are in your basis, that's the dimension of your vector space. All right, great job, everyone.